units. So in 1999, NASA lost the $125 million Mars Climate Orbiter. What happened is it descended too far into the Martian atmosphere and burned up. So of course there was an investigation. The conclusion was the root cause of the loss of the spacecraft was a failed translation of English units into metric units. Somebody was doing calculations with inches, and somebody else was doing centimeters, and they didn't communicate. Now, thankfully, the errors that we make with units don't cost $125 million. But units are very important, and they're going to be very important in this class. So a unit is a standard quantity used to specify a measurement. And there are two common systems, the metric system, which most of the world uses, and the English system, which we just stubbornly keep using here in the United States. What scientists use is actually called the International System of Units, or the SI system. It's based on the metric system, and in my opinion, the differences between the metric system and the SI system are not even worth talking about. So base units in the SI system, so these are the different quantities that can be measured: length, mass, time, temperature, amount of substance. These are also there, but we won't be talking about them. So the unit is meter, kilogram, second, Kelvin, and mole, and these are their symbols or their abbreviations. There's a question on the worksheet about metric units. It is a good idea to have a clue as to how big these units are. I'm not going to quiz you on this, but if you know how big a meter is, and you do a calculation and you come up with this basketball player is 7 meters tall, if you know how big a meter is, it's about a yard. Nobody could be that tall, right? So that alerts you that, hey, wait a minute, I need to go check my math because something went wrong here.
Isn't Hagrid that tall?
They can be 7 feet tall, but not 7 meters, right? Because 7 meters is about 21 feet.
No, Hagrid isn't that tall.
No, Hagrid's not that tall. Not even Hagrid. So meter, approximately a yard. Mass is a measure of how much matter is in something. The SI unit is the kilogram. We use the gram a lot in chemistry because it's a smaller unit and it's more appropriate for the amounts of stuff that we use. A kilogram is about 2.2 pounds, right? So about twice as big as a pound. Mass and weight are different. Mass is amount of stuff. The weight is a measure of gravity pulling on something. So if you stay on the Earth, mass and weight can be used interchangeably. If you're going to travel to the moon, then we have to specify whether you're talking about mass or weight. So the gram is what we typically use in chemistry. A gram, 5 grams is about the mass of 5 cents. So a nickel is about 5 grams, so that gives you an idea of how big a gram is. SI unit of time is the second, just like the second that we're familiar with, but they tend to just use seconds, and they don't go into minutes and hours because those are not related by factors of 10, so we'll just stick with seconds. And there's the definition if you're curious. The SI unit of temperature is the Kelvin. Temperature is a measure of the average kinetic energy, how much the atoms or molecules are wiggling. Temperature is also going to determine which direction thermal heat transfer is going to occur. The heat always goes from the hotter object to the colder object, right? If you put an ice cube in a cup of coffee, the coffee's going to get colder, the ice cube's going to get warmer. It never goes in the reverse where the ice cube gets colder and the coffee gets hotter. Right? It never does that. So the Fahrenheit scale is what we are accustomed to in the United States. You know, they say it's 104 degrees outside. They mean degrees Fahrenheit. And this scale is based on let's not even talk about that. The Celsius scale is the one used by scientists. It's also sometimes called the centigrade scale. And this was based on assigning 0 to the freezing point of water and assigning 100 to the boiling point of water. On the Fahrenheit scale, water boils at 212 and freezes at 32. So, like most English units, the numbers there are kind of wonky, whereas here we have 100 and 0. Both of these are going to allow for negative temperatures. So there's a third scale called the Kelvin scale. On this scale, you cannot have negative temperatures, and we'll see that that's really important when we start to do gas law calculations. So on the Kelvin scale, 0 is assigned to the lowest possible temperature, the absolutely coldest temperature that could exist, which is where the molecules of that substance would not even be vibrating. So that's called absolute 0. The units here are kelvins, they're not degrees, but the unit size of a Kelvin is the same as a Celsius degree. What's different is where 0 is. Celsius scale, 0 is at the freezing point of water. On the Kelvin scale, water is going to freeze at 273 Kelvin. So we do need to be able to convert between these different temperature scales. And unlike most of the conversions that we're going to do in this class, these require equations to do that conversion. The Celsius and Kelvin scales are quite easy to convert because Kelvin is just the Celsius temperature plus 273.15. The relationship between Celsius and Fahrenheit is a little more complicated because the degrees are different sizes and 0 is in a different place. I will give you these two equations on exams. I don't expect you to memorize those. So let's do an example here. Gallium is a solid metal at room temperature, but will melt to a liquid in your hand. The melting point of gallium is 85.6 degrees Fahrenheit. What is this temperature on the Celsius scale and the Kelvin scale? So they're giving us some information. They're telling us that we have a temperature of 85.6 degrees Fahrenheit. And then they're asking us for other information. They're wanting the Celsius temperature and the Kelvin temperature. So converting temperatures, we need to use those equations. So we can convert Fahrenheit into Celsius. So to do that, we're going to use that equation. Celsius is equal to Fahrenheit minus 32 divided by 1.8. So I'm going to plug this Fahrenheit temperature in. 85.6 minus 32 and divide by 1.8. I'm going to do this on my calculator. You need to be a little bit careful. Probably a good idea to use parentheses up there so that you don't end up doing something else and getting the wrong answer. So my calculator is showing me 96.48. And that would be degrees Fahrenheit. So we're talking about something that melts in your hand. What's your body temperature in Fahrenheit? 98.6 on the inside, right? So in your hand, 96 degrees, that's reasonable, right? So we talked about significant figures already, even though it comes after this in the chapter. Here, with this equation, we see that we have two different operations. Yeah, question?
Don't you read Celsius?
Yeah, I do. Thank you. Thank you. But that's wrong. What did I do?
Hot, I don't know.
What did I do?
I got 29.7.
You know, I wish I could say that I do this on purpose, but I don't. 85.6. Oh, I multiplied instead of divided. Yeah.
Oh, okay.
Okay. I wouldn't have this problem if I looked at what I was doing.
Because I was thinking, isn't such and so lower?
Yeah.
I was like, why is it so high? That's a Fahrenheit number.
Yeah. So I make mistakes all the time, and so please question me. Okay. 29.77 repeating degrees Celsius. Okay. I think I put Fahrenheit because that would make some sense, but oh gosh, so soon.
Because you got the number.
Yeah.
The number threw you off.
Okay. So this is a great illustration of why it's always a good idea to do your calculations twice. Do the calculation, press clear on your calculator, and then do it again. Because if you're making just kind of a random error like this, you're probably not going to do it twice in a row. So then what's going to happen is you're going to get two different answers. So then what do? You do it a third time, right? And we're going for best 2 out of 3 most of the time. Okay, so I was going to talk about sig figs. We have subtracting and dividing, and we learned on Monday night that gets a little icky with the significant figure rules. With temperature, we can kind of just go around that. For temperature, what we can do is we can look at our original temperature and ask, well, where's the last decimal place? There's one decimal place here. It's, to the nearest 0.1. And so then we're going to round our answer to the same decimal place. And the reason that works is because a degree Fahrenheit and a degree Celsius are very close to the same size. So I'm going to keep one decimal place, and I should call that 29.8 degrees Celsius. The sig fig rules will almost always give you the same result. Yeah?
So with the temperature, we just keep the last decimal points of it?
You round it to the same decimal place as the original number
Okay, and that's with multiplication and division?
for all temperature conversions.
Okay.
Yeah. It's just a lot easier.
In addition to?
Yeah, it's going to come out to be the same. That actually is the rule for addition. And if you're curious about that, I'm happy to talk to you more about that. Okay, so that's the first answer, the Celsius temperature. And then it also wants the Kelvin temperature. Well, we have that relationship. The Kelvin temperature is equal to the Celsius temperature plus 273.15. So I did this first calculation, and this is my final rounded answer. Should I use the rounded answer to do another calculation or the unrounded? Unrounded. So I'm going to use the unrounded one. So I've got 29.77 repeating plus 273.15. And that's going to give me, 302.927 repeating. So our original number had one decimal place, our original temperature. So I'm also going to round this to one decimal place, and we're going to call that 302.9. Kelvin. It's tempting to say degree Kelvin, but it's not a degree, it's just a Kelvin. Any questions? There's some practice doing temperature conversions on the worksheet as well. There, I finally got the right answers. We did mention scientific notation a little bit on Monday night. If you need a review of that, you can see Appendix 1A in the book. There's also a dynamic study module on Mastering Chemistry that will bring you up to speed on scientific notation, or feel free to ask me during lab. The scientific notation lets us express really big numbers or really small numbers in a much more compact way by using factors of 10. Basically factoring out tens. The SI and metric systems use the same idea with their units. We can't just have one unit for length, right? So inch is a unit of length. Why don't we measure the distance between Fresno and Sacramento in inches? It'd be a huge number, right? It'd be a huge number. What do we use instead? Miles. We use a larger unit for larger distances, smaller units for smaller distances. Generally, you want a unit that's close to the size of what you're measuring. So instead of having to deal with inches and feet and yards and miles, like we do in the English system, in the metric and SI system, everything is meter, and it's just multiplied by a factor of 10. So there are these prefix multipliers. For an example here, kilometer. So that's meter with the prefix kilo. So kilo stands for 10 to the third. So 1 kilometer is 10 to the 3 meters. So we make the sizes of the units bigger or smaller by factors of 10. We use the same prefix multipliers for all the units, and so there's a lot less to remember. So we always want to choose a prefix multiplier that's going to be similar in size to what we're measuring. There's also some practice about this on the worksheet. These are all the prefix multipliers that are listed in your textbook. I think there are more. But as I mentioned on the information to memorize, kilo, centi, oops, that's not what I wanted. Milli, micro. Those are the 4 that are most important in chemistry. So if you can't memorize all of them, at least get those 4. So kilo is abbreviated with a lowercase k, and it stands for 10 to the 3. I don't recommend using these because aside from the ones in the middle, there's just too many zeros. So let's memorize these as factors of 10. 10 to the 3, 10 to the minus 2, minus 3, minus 6. Okay, so how long is 4.5 megameters in meters? Well, what does mega stand for? What does mega mean? 10 to the 6. So 4.5 megameters is the same as 4.5 times 10 to the 6 meters. So instead of writing the letter, I can write what it means. So this is just an abbreviation for times 10 to the 6. 7.13 times 10 to the minus 9th liters is equivalent to how many nanoliters? Well, what does nano stand for? Nano sounds like 9, 90, 10 to the minus 9. So what I can do is instead of writing times 10 to the minus 9, I can write the lowercase n. It really is a beautiful system. You just need to become friends with it. You need to work with it until you see how it works, and then it's just so much easier. I mean, do you remember how many feet are in a mile? Anybody? It's 5,280. I remember that one. I can't remember the yards in a mile. You know, teaspoons to tablespoons, tablespoons to gallons. It's all crazy numbers. Metric system is just factors of 10. Keeping it simple. So we have those basic units, measurable quantities, and we have derived units, which are combinations of other units. And these are going to be things like measuring speed, rate of travel, like miles per hour or meters per second. It's got time and a distance in it. Or volume. So volume is a measure of space, and we know that any unit of length, when we cube it, becomes a unit of volume. And so this is actually a picture of me in the Science Museum in Oslo, sitting in a cubic meter. So meter that way, 1 meter this way, 1 meter that way. So hopefully we remember from geometry that the volume is equal to the length times the width times the height. So 1 meter times 1 meter times 1 meter is 1 cubic meter. So you can take any of those length units and cube them, and those become volume units. We tend to have special volume units for measuring liquids. Just like in the kitchen, you don't measure milk in cubic inches, right? It's not very practical. You use fluid ounces, right? So when we're measuring liquids, we'll typically use the liter and the milliliter. So here we have a cube made of smaller cubes. So each of these cubes is 1 centimeter on a side. So what's the volume of this little cube? 1 centimeter times 1 centimeter times 1 centimeter, right? So that's 1 cubic centimeter. Whoops. So 1 cubic centimeter also has the name milliliter. In medicine, they call it a cc for cubic centimeter. So here we have a bigger cube that is 10 of those little cubes across and 10 high and 10 deep. So the volume of that big one is 10 centimeters cubed, right? So that's going to be 10 to the 3 cubic centimeters. And that is called a liter. So a liter is 10 to the 3rd cubic centimeters. So a liter is 1,000 times larger than a milliliter. A milliliter is 10 to the minus 3 liters. So this table on 1.3 in your textbook gives mostly relationships between English and metric units. The nice thing about the metric system is that converting units within the metric system, you don't need a table like this because it all uses the same prefixes. So you'll learn the most important prefixes and you don't need a table. But going between English and metric, you're going to need a table. And then sometimes, you'll have to convert within the English system and you have to look stuff up because you don't remember how many quarts are in a gallon. But these are conversions for length, for mass, and for volume. One that they leave out, I guess it's supposed to be obvious, but it's not obvious to Chem 1A students. A cubic centimeter is the same as a milliliter. There are two different names for the same thing. Okay, so if you have something in cubic centimeters and you need to convert it into milliliters, you say, well, those units are the same. It's just the same number of milliliters. There are questions in the homework, there are questions on worksheets where you're going to need to do unit conversions. And we have these handouts over here, and I put digital copies of them on Canvas. Students like them a lot. The yellow one has a whole bunch of conversion factors on it. This is way more than you need for my assignments, okay? So yeah, you can use that. I would encourage you to just use these. The other thing, of course, that you could do is you could ask Google, right? Google will do anything for you, right? Yeah, question?
Is that the only direct conversion between liters and liters?
Between liters, well, milliliters and cubic centimeters, yeah. So the thing about asking Google to do unit conversions for you, I mean, that's fine if you're trying to bake a cake and you need to do something quick. I'm going to teach you how to do something called dimensional analysis, which is using the units to guide calculations. The reason I'm teaching you that is not just so that you can convert units. It's so that you can do stoichiometry, which is a huge part of chemistry. So when we're doing unit conversions, if you kind of get around that by using Google, you're not going to learn the method, and when we come to stoichiometry, you're going to be in trouble, okay? So on the worksheet we're going to do today, there's one part where it's giving you things you have to convert, the units, and in order to get credit for it, you have to use dimensional analysis, and you have to use the path that I gave you. So everybody's is going to look the same. And, other times I'm not going to do that, but I want to make sure that you all start to understand dimensional analysis. Another derived unit is density. So density is the mass of an object divided by its volume. So shorter, we often say D equals M over V, mass over volume. So these are derived units. There's not just a special unit for density. It's going to be a combination of units. So grams per milliliter or grams per cubic centimeter, commonly what are used for liquids and solids. So density is a physical property that depends on temperature. This is also on the worksheet. It's a question. So if density depends on temperature, that means that one of these things, mass or volume, depends on temperature. Does the mass of an object change with its temperature? The mass is a measure of how much matter is in the object. Or does the volume change? It's the volume that changes. For things like gases, the volume changes a lot with temperature. For liquids and solids, the change is much smaller. But this is why anytime you look up densities, they're going to tell you a temperature. So here, these are densities at 20 degrees Celsius. The densities are going to be slightly different at other temperatures. You do not need to memorize these densities. The only one that there'd be any point in remembering is this one. Water at 4 degrees Celsius has a density of 1 gram per cubic centimeter, which is the same as 1 gram per milliliter. So there will be times when you'll use that. Other times, like in lab, we'll actually be looking up the temperature of our water and what its density is. So there are two kinds of properties other than the physical and chemical properties. There are intensive properties and extensive. So an intensive property does not depend on the amount of substance. An extensive property does depend on the amount of substance. So you can think of intensive like intrinsic, extensive like external, right? An intensive property is going to be something like the density or the melting point. The density of water is 1 gram per milliliter. If you have more water, the mass is bigger and the volume is bigger and the ratio is still the same. Intensive properties can be used to identify substances because it doesn't matter how much you have. An extensive property is going to change depending on how much you have. So these are things like mass or length or volume. The mass of a gallon of water is much greater than the mass of a teaspoon of water, but the densities are the same. So extensive, intensive. So here's a fun problem. When I was in school, we called these story problems. I think you call them word problems now. Doesn't story sound friendlier? It's a story, right? Anyway, there's lots and lots of word problems in chemistry. And there's like 2 groups of people in the world. One that think that word problems are kind of fun, and everybody else who hates them, right? So if you're in the hate word problem camp, you're in good company, but we do have to learn how to do word problems. And even though it's not your favorite thing, even though you might not feel that you're any good at it, you can become better at it, right? You can learn how to do it better. And so I'm here to help you with that. First thing to do is to read the whole story. So a man receives a platinum ring from his fiancée. Before the wedding, he notices that the ring feels a little light for its size and decides to determine its density. He places the ring on a balance and finds it has a mass of 3.15 grams. He then finds that the ring displaces 0.233 cubic centimeters of water. Is the ring made of platinum? So you read the whole thing, then go back and highlight the numbers. Usually all the numbers are important. So here we have a mass in grams, we have a volume in cubic centimeters. Those are the only numbers that show up. And then we want to see, what are they asking us to find? Well, is the ring made of platinum? Okay, well, we need to find the density. It doesn't come out and say what is the density, but it gives us a hint. This guy decided to determine its density. So what we need to do is find the density, and then to answer this question, we'll compare the density of the ring to the density of platinum. If the ring is made out of platinum, those numbers should be really close to each other. Okay? So this is what we have to do. We have to find the density. When you're oops, I didn't mean to do that. There we go. When you're calculating density, you're going to use the equation density equals mass divided by volume. That is the only time you use the density equation. If you're calculating mass or calculating volume, I'm going to show you a better way. You use the equation to calculate the density. So we need the mass of this object and its volume. Well, what does this give us? The mass. It's in grams, yeah. Mass of this in grams. Okay, so let's write that down. Always include the units, 3.15 grams. And the volume, it doesn't specifically say that, does it? It says he finds that the ring displaces 0.233 cubic centimeters of water. What kind of a unit is cubic centimeters? It's the same as milliliters, which is a volume unit, right? So this is the volume. What do they mean by the displacing business? Well, the water rises, yeah. So there's a story of, who was it? He said Eureka. Do you remember?
What?
The guy in the bathtub with the water. Displacement of, no.
I have no idea what you're talking about.
there was this like old Greek philosopher or something. So, bathtub full of water. He gets into the water. Well, not sure what that was. He gets into the water. What happens? The water spills over the top. You fill the don't do this at home. Fill the bathtub all the way to the top and then climb in. What's going to happen? A whole bunch of water's going to spill out. Why? Because you pushed the water out. You displaced it. Your volume is pushing out an equal volume of water. So one of the ways you can measure the volume of an irregularly shaped object is using water displacement. So you can take a graduated cylinder and put some water in it and make a note of where the level of the water is. Let's say this is 10.0 milliliters, right? And then we put a rock in it, and what happens to the water level? It goes up. Okay, just to make the math easy, now it's 12.0 milliliters. The change in this is equal to the volume of the rock. The volume of the rock is displaced. Okay, so that's what they're talking about. Okay, so we have the mass, we have the volume, we can do the math on our calculator. 3.15 divided by 0.233. My calculator is giving me this whole big mess of numbers. Oops, 1.93133. Okay, we already learned about significant figures, right? How many significant figures does 3.15 have? 3. How many does 0.233 have? Also 3. So our answer here, we're dividing, so the answer should have the same number of sig figs as the other number with the fewest. They both have 3. So our answer should have 3 sig figs, right? So I'm going to keep 1, 2, 3. I'm going to keep up to this one. So when you're writing this down, you don't actually have to write out all the stuff that your calculator spits at you. It's good enough to write 2 extra digits. So if I was thinking ahead a little bit as I wrote this down, I would just write down that much. You always want to write down those 2 extra digits, especially in lab, when you're going to be putting stuff into the computer, because it's going to be really picky about stuff. So I'm writing down extra digits, and then I'm going to round it. So here I've got a 5. The next digit is a 1. So this rounds down. And so this is 13.5. And what are the units? Grams divided by cubic centimeters. Nothing cancels out. There's no converting. It's one of those derived units. We've got grams divided by cubic centimeters. So here we've got grams divided by cubic centimeters. So that's the density of the ring. We need to compare that to the density of platinum to see if the ring is platinum. How do we figure out what the density of platinum is? We go to the density table and look it up. So here's platinum down here. Platinum's 21.4. 13.5, 21.4, not even close. So is this platinum? No, it's not. So the answer to this whole question then is no. You should always make sure that you're answering the question. Sometimes there's things that you have to figure out in between, but the ultimate question was, is the ring made of platinum? And the answer is no, not 13.5. So follow-up question. The woman in this example is shocked the ring is fake and returns it. She buys a new ring, has a mass of 4.53 grams and a volume of 0.212 cubic centimeters. Is this one platinum? Well, you need to find the density, right? I'll skip all the highlighting. The density is the mass divided by the volume. There's our mass. There's our volume. Now, as I'm writing this down, I'm thinking about it. 3 sig figs, 3 sig figs. This one needs 3 sig figs. So there's my 3 sig figs. I'm going to write down the next 2 digits. And when you do those next 2 digits, you don't need to worry about rounding the last one. Just write it down, whatever it is. And then we'll round this. So here we're dropping the 6. So this is closer to 21.4 grams per cubic centimeter. Is this one made out of platinum?
Yes.
Yeah. It's, maybe we don't quite remember what that number was. 21.4. What if the density was 21.3? That would still be platinum, because this is a measured quantity. This is not an exact number. There is uncertainty in the last decimal place. So if you have something that's within 0.1 of that, it's going to be platinum. Now the paper's going to sink. Another question. The density of copper decreases as the temperature increases. This happens for most substances. Which change occurs in a sample of copper when it is warmed from room temperature to 95 degrees Celsius? Does the sample become lighter when you change the temperature? Does the mass change? No, the mass doesn't change with temperature. Does it become heavier? No, if it can't become lighter, it can't become heavier either. So we need to remember that the density is the mass divided by the volume. So this says that when the temperature increases, then the density increases. So we're warming this from room temperature to 95. The temperature's going up, which means that the density is going up. The mass isn't changing. It's got to be the volume that's changing. If the volume was bigger, would the density become bigger? If I take this same number and divide it by a larger number, it becomes smaller, right? What if I take this number and divide it by a smaller number? Then the density becomes larger. So the volume must get smaller. The sample contracts as it heats up. No, I did that wrong. That's why you guys were looking at me like that. These are confusing. So this is where I went wrong. I was talking about the temperature increasing, but it says the density decreases. You really, I don't recommend trying to answer a question like this just in your head. You should draw some pictures or something, because even then you might get it wrong. Okay, so the density needs to get smaller. The mass is the same, so what's happening to the volume? It's getting bigger. Okay. Well, that was awesome.
So when you say contracts, does that mean?
Contracts is getting smaller. Yeah, expanding is getting larger. And if you're taking an exam and they use words like expand and contract instead of bigger and smaller, and you're not exactly sure that you know what that means, feel free to come up and ask me, okay? I got rid of a question I used to ask on the first exam because it talked about dew on the grass. And I found out a lot of people don't know what dew is. That's at night when it gets chilly, the grass gets wet, right? That's called dew. I realized a lot of people don't know what that is. Okay, so we're not using that question anymore.